Hello again. I'll be talking now about my work in advances in soft sensors and actuators within wearable mechatronic devices for motion assistance. And so even though we at our lab work on all aspects of mechatronic system design, I'm going to focus this specifically on the sensors and actuators to fit the hardware component of this workshop. And this work is happening at the Wearable Biomechatronics Laboratory at Western University in London, Ontario, Canada. And it's a lovely space where we have lots of room for developing these wearable textile-based devices. So just to give you the motivation for our work, we work on developing technologies for people who suffer from musculoskeletal injuries, for example, when they have suffered from from playing sports or motor vehicle accidents, or those that develop from neurological diseases. And some of the applications we're working with are dealing with people who go to outer space and are exposed to low gravity environments, which also results in musculoskeletal issues. And what all of these have in common is that there's a disconnect between the brain and the neurons and the muscles that requires rehabilitation in order to recover the activities of daily living. And so we develop mechatronic systems for these purposes. And of course, robots are mechatronic systems. We have sensors within the mechatronic devices. We have actuators that provide the movement. And there's always a control system that takes the information from the sensors, provides movement to the actuators, right? That would be the standard mechatronic system. When we're talking about wearable mechatronic devices, we have the human within the loop. And so we have information that is coming from the sensors regarding what's going on with the human body. There is potentially a direct interaction between the human and the control system. And there is a definite interaction between the forces from the mechatronic device to the human and from the human to the actuators as well. And so this is sort of like the general issues that we're dealing with when developing mechatronic systems. And although I could spend probably 2 hours talking about control system design and human modeling and interpretation, I'm going to focus on the sensors and the actuators. So let's start with the sensors that we use in these devices. And so because we're talking about wearable systems for motion assistance rehabilitation, the majority of the information needs to come from muscle activity sensors, right? And so if you've ever worked with these devices, you know that the signals that we get are very noisy, and there's a lot of processing that is required in order to fully extract information about what's actually happening with the muscles. But it still is the most essential sensor that we can have in these devices. We have also used EEG or electroencephalography to identify the brain activity that is directly related to the motor movement. And so there's locations on the scalp that give us this information related to motor motion. And so we can potentially identify things like intention or what the user is trying to do, as opposed to what is actually happening at the muscle level. So EEG on its own wouldn't be sufficient, but a combination of EMG and EEG and together with motion measurement, then that would be the ideal. Motion measurement is something that is probably the easiest one to get, and to get very, very accurate information. These are sort of like the standard electromyography, electromagnetic tracking, I'm like EM, the electromagnetic tracking, motion, and camera-based systems that provide very accurate tracking of the human body. But it's harder to get things like that within a wearable system. So usually what we do is that we get inertial measurement unit sensing. So you can develop them very, very small. You can distribute it throughout the body. And this is probably the most important way of getting motion information, although it does require quite a bit of calibration. And so this is how we started. We developed a motion sensing sleeve that provided 23 degrees of freedom of the upper body using 23 inertial measurement units. And I had the opportunity to participate as one of the participants in this study and had to wear this device for 48 hours. And it was the most uncomfortable thing that I've ever had to wear in my life. Even though we try to make it super comfortable, soft materials, breathable materials, it was itchy, it was hot, it was heavy, even though it was relatively light. And so we're like, this was sort of like an eye-opening point for me, because I was like, we need to do something better. We need to do things differently, so that we can actually incorporate these devices into people's lives, so that we can gather more data. And this is like, I'm a relatively healthy individual. If you're dealing with somebody that has a musculoskeletal injuries, you can imagine how difficult this would be. And so we got into the field of textile sensors. And also, to make it more accessible, we're using low-cost textile sensors. So instead of developing sensors that are based on chemical processes that require expensive equipment to manufacture, we are focusing on using standard manufacturing techniques such as sewing and knitting and crocheting and embroidery, so that we're basically going back to the way textiles were built, but incorporating conductive materials within them, so that we can use them to gather motion information. And so the first types of sensors that we developed were weaved sensors. So you can sort of see here that you have the loom on the left, you have the material on the middle, and then the sensors that come out are on the right. They look like little caterpillars. But we get a lot of, when we stretch them, we can get a significant change in the resistance. And I'll show you how they behave in a minute. These are the crocheted sensors. So even lower cost, because all you need is a crochet needle to build them. And you can see the one on the bottom left is the crocheted sensor without stretching. We stretch it onto, it looks like the one on the right. You can see the conductive material embedded within the crocheted sensor. And as I play this video, you're going to see how we test them. So the pink, this is a pink sensor. You can sort of see the pink on the lower right of the video. And this is a setup that allows us to stretch it and contract it and stretch it and contract it automatically for many, many cycles. So this is something that we use for the testing. So I'm going to show you some of the results that we've gotten from this. So there's a lot of information here, so I'm going to walk you step by step. So this, looking at the first row only, this is the silver-plated fully crocheted sensor. So that means that there's silver-plated conductive material that has been crocheted together when the sensor was manufactured. And what we have on the colored bars is the working range within the full range of motion of the sensor. So when we stretch it from 0 to 100%, it is the beginning and the end of that black line. And the colored portion is how the behavior of the sensor itself within that. So if you see at the beginning, so we started with the second cycle, 11th cycle, 30th cycle, 75th cycle, and 100th cycle, you can see that there's little variability, but some variability from the beginning to the end in terms of what this working range is. And we can also see that the working range is relatively wide with respect to the full 0 to 100%. And you can see that it's sort of towards the middle of the full range of motion. So this is ideal. This is what we would like to be able to get. So we built 3 of these silver-plated sensors. And so you can see the behavior here. It's similar sensor to sensor. And then we compared it to other types of sensors that we were manufacturing. So this is a stainless steel fully crocheted sensor. So similarly made, but we used stainless steel instead of silver-plated conductive thread. And you can see the huge difference in the behavior, right? At the beginning, the working range was not too small. It was a good amount of working range, sort of towards the beginning of the whole stretch cycle. But you can see how much it changed towards the end. So it shrunk quite a bit with only 100 cycles. So if we were to test 3,000 cycles, you can see that we probably would end up with no working range. And so that is not an ideal sensor. This next one is also silver-plated, but we stitched the conductive material into the crocheted base. So it wasn't crocheted, it was stitched in. And the behavior is relatively good compared to the silver-plated fully crocheted sensor. We can see that we have like wide working range, and it's sort of consistent sensor to sensor, consistent from the beginning to the end. Now, comparing that to the weaved sensors that we talked about before, we actually thought the weaved sensors were really good, and I'll explain why in a minute. But when you compare it here, you can see that the working range is quite small in comparison. And it doesn't matter. It doesn't change too much cycle to cycle, but because it's so small, then it's very limiting. So the reason why we thought that the weave sensors were good is that these are other metrics that we get from the sensors. We have the gauge factor in the first column, the hysteresis, and the linearity. We want the gauge factor to be as high as possible to get good sensitivity. The hysteresis, we want it to be as low as possible so that it doesn't change too much going up and coming down. And we want the linearity to be as close to 1 as possible so that it is the most linear. So we thought that our weave sensors at the bottom were pretty good because we had a gauge factor of over 5, hysteresis was very low, and the linearity was almost 0.9, so pretty good. But because of the behavior of that working range, all of these are measured within the working range. So even though these values were good, they're measured only on that tiny little bit of the working range, which doesn't give us a lot of practical use, right? So from the other 3 sensors, we can see that the top one ends up being the best because it has the highest gauge factor, the lowest hysteresis, and the best linearity, right? So that's sort of like the types of tests that we're doing in order to try to find different materials and different patterns to give us the best types of sensors. And now the other type of sensor that we're using is the embroidered sensor. This one is a little bit more expensive to manufacture because we do need an embroidery machine. But you can see here the silver thing in the bottom is our embroidered sensor. You can see how much the resistance has changed by just simply stretching it. You can also see the pattern of the embroidered. And what you see here is the actual sensors being manufactured, right? So this has proven to be the best one of the ones that we've gotten. And when you see the video that I'm going to run here on the right, you can see that when the sensor is stretched, it gives us a really great response. And so if we attach this to a wearable garment, then just the movement would create this level of stretching in the fabric, and then we can get pretty good results. Something that we've discovered is that it's not enough to develop sensors and using standard data acquisition systems. We really do need to develop our own custom data acquisition systems that are specifically tailored to the sensors that we are using. So this was a data acquisition system that was just recently developed for the embroidered sensors and significantly reduced the size of it, but also increased the sensitivity and reduced the noise. So it really, really makes a huge impact. So in terms of sensors, I understand that not all of you work in wearable sensors, but it's important to consider because these are applicable to any kind of physical technology that would require measuring what's going on in the body. We're going to continue testing new materials. We're going to figure out ways to evaluate the artifacts and the interference and incorporating machine learning algorithms to really differentiate the voluntary movement or the movement that we're trying to collect, and then what is caused by other types of interactions and other interferences. We're going to use these same techniques to create our own electrodes, and we're going to then integrate them into sleeves, gloves, and shirts, and this is sort of ongoing work as well. And then combine them in different garments in order to get multi-axis sensing. One cool thing that is happening, if you have heard of Myant-X, it's a company in Toronto, in Canada, and they develop really, really cool electrodes. And so we're starting a collaboration with them. They make knitted electrodes. And we're hoping that together with our motion sensors and their electrodes for muscle activity, then we can come up with some really great designs for tracking human motion. So that's on the sensor side. The actuator side is shorter, I promise. But for the actuation, so I just want to start by saying that there are no good actuators right now for wearable devices. And I'm going to talk about what we've done, which I recognize that it's not ideal, but there's some hope, I hope. So this is how we started. We started using standard electric motors about 10, 12 years ago. And obviously, we immediately realized that this is way too heavy. You need one motor per degree of freedom. We were looking at the wrist, the finger, and the thumb, and this is basically the size of a device, right? So this is just not appropriate for a wearable device that is for supporting people with musculoskeletal disorders. So of all of the actuators that we've evaluated, the best one that has shown promise is called the twisted coiled actuator, which you might have heard of. And so these are actuators that are, it's a standard nylon fishing line that is coated with a conductive material, and then it gets hyper twisted. You can see here the setup that we use for the hyper twisting. And this is what happens when you hyper twist it and then you fold it onto itself. And you can see how it creates this cord. So super, super light, super inexpensive to manufacture. And then when we put a current through it, it contracts. It contracts actually quite a bit. So you can see here sort of like this, the behavior of you can create different sizes, different lengths, different thicknesses. And when we put a current through it, the actuator is sort of holding that weight. You can see that it contracts up to 10% of its length, and it lifts quite a bit of weight. I think here it's lifting about 4 newtons, which is significant for the power, the weight of the actuator itself. So we use electricity to heat it up, and of course, then it needs to cool to expand again. And so some of the work that we've had to do is related to how we can cool it. So this is a setup that we developed just to test the optimal way, the optimal scenario if we had all of the cooling power that we needed, obviously not on a wearable device. You can see that when it's the twisted coiled actuator is lifting and lowering that wrist phantom, and it moves it at a very good pace, right? Like the extension and the contraction is a very good frequency for mimicking voluntary motion. But that is using a setup that has really good cooling capabilities, right? Like I think we were using compressed air for that. But in order to make them more wearable, we are working to develop twisted coiled actuators that get embedded within channels in the fabrics. And so we have 3D printed channels that are combined with tiny micro pumps that blow air through the channels. And so when we incorporate it all together, it ends up being something that is fairly wearable. We are continuing in this line, trying to come up with better ways of making sure that the airflow is established. The micro pumps are okay, but they don't provide enough airflow for a standard frequency for voluntary motion. But we are definitely creating different ways of embedding them within the different fabrics. 3D printing onto fabrics has proven to be really good, but we can also just sort of sew the channels within there. So as next steps in actuation, we are going to continue developing cooling mechanisms. We're going to continue exploring other types of actuators as well. So if anybody hears about actuators that can be wearable, please let me know. I'd love to hear about them. And combining different types of actuation is actually also important, right? So you could have an electric motor, and then you could have some other twisted coiled actuators combined with some passive actuation to provide like bulk forces in some directions. And then we have developed so many different models for the behavior of the twisted coiled actuators, combined with human biomechanics models, combined with just standard friction and movement of tendons and sheaths that characterize the movement of the human body, of the upper limbs. And so combining all of those to get one big model that can be used for better control. So those are our next steps. And we have a wonderful team of students over the years. And I just wanted to thank them and thank you for your attention. I'm happy to take any questions.